Someone did not do a good job erasing the board.
Oh yeah. Yes. I'm starting with 75 cents. Right, I got 75 cents. Yeah, I just think there's something. All right, good afternoon, everyone. So just before I forget, let me just mention that I am in the middle of preparing the first assignment, so that will probably be posted to the course website sometime this week, maybe today or tomorrow is my best guess. So what I want to do is I want to just do an example of some of the things we were talking about. We came up with these methods for calculating expectation values for functions of x, where x was going to be governed by some kind of probability density p of x. And the general method was just fairly simple, actually. The procedure, anyways, is to take your function of x, multiply it by that probability density, and then integrate over all the possible values of x. The only thing you really have to be careful about is making sure that you integrate over the domain of x that is governed by your probability distribution. Very often, your probability distribution would extend from plus minus infinity, but that's not always necessarily the case. So if we do take that definition for calculating expectation values of a function of x, we could just set f of x equal to x, and the way we would calculate the expectation value would just take x times p of x and integrate. Likewise, for x squared, we just put in an x squared there. Those two are useful ones to think about because, as we showed last time, we can then figure out the standard deviation or the spread of, say, x by looking at the difference between the expectation value of x squared and the expectation value of x, and then square it. So what I want to do first today is I want to do an example where we apply these techniques. And so I'm going to try to do an example that is relatively straightforward, but also has some relevance to actual physics. So the distribution that I want to think about is the exponential distribution. And what I'm going to do is I'm going to say that this is defined for t greater than 0, or let's say greater than or equal to 0. So what does this have to do with any kind of physics? If you have like a sample of unstable particles that are decaying at some rate, then the size of the population is governed by this kind of probability density. So in the third year lab, we have one experiment where we detect muons and we measure their lifetime. And when you collect the data, the distribution of lifetimes that you measure follows this kind of exponential distribution. And so I want to work out some of its properties. And so we're going to do 4 parts to this problem. And so let's get started. The normalization constant. So for normalization, we are going to require that if we integrate, this time our probability density is a function of time. So let's imagine we do this experiment. So we detect a muon, and then we sit and we watch it until it decays, and we measure how long that happens. And then we do that over and over thousands of times, and we plot some distribution, some histogram of those lifetimes. So what we are going to require that is, what is the probability integrated over all possible times from 0, the moment that we detect the muon, out to infinity? So the muon must decay somewhere between when it was detected and an infinite time later. And so we require that this is going to be equal to 1. And so this is our normalization requirement. So all we have to do is put in our probability density, this exponential distribution, and complete the integral. So we require 1 is equal to the integral 0 to infinity a of e to the minus t over tau, and we're going to integrate over time. I think that was the right one. Yep. Okay, this is really pretty trivial. Just integrating an exponential returns the exponential back again. So we'll get a. And then when we do the integral, we'll get a minus tau coming out. So we'll have a factor of minus tau. And then we have e to the minus t over tau comes back. And we have to just go between our 2 limits of 0 and infinity. Okay, and so this is equal to minus tau times a, e to the minus infinity minus e to the 0, and e to the minus infinity is 0, e to the 0 is 1. And so we end up getting a minus and a minus sign that cancels. And so we end up with 1 is equal to a times tau, or a is equal to 1 over tau. And so therefore, what we could say is that our normalized probability density is going to be 1 over tau e to the minus t over tau. So this is the normalized probability density. So if you remember, what we said is if we had a probability density, then p of x dx was equal to some probability of finding your particle between x and x plus dx. And so we said if that's the case, then p of x times dx has to be unitless. Dx has units of, say, length. So p of x has to be 1 over length. Here we have a probability density as a function of time. And so its units has to be 1 over time. And there it is, the 1 over tau. Tau has units of time in order for this exponential, the argument of the exponential, to be dimensionless. All right. So the next thing we were going to do is we're going to try to find the expectation value of not x, of t. So what is the average decay time of this population of muons that we're going to measure? Well, all we're going to calculate is t times b of t integrated over all the allowed times, which in this case is 0 to infinity. Okay, so we just worked out our normalization constant, so we'll use that. We'll get a 1 over tau coming outside the integral. 0 to infinity, t e to the minus t over tau dt. All right. So how are we going to evaluate this integral? What's the technique we're going to use? Yes, that's right. So the integral of u dv is equal to uv minus the integral of v du. Let me emphasize something that lots of people remember this, but let me emphasize something that they often forget. So if I'm going to integrate from a to b, then I have to integrate from a to b over here. The thing that people omit is that this u times v has to be evaluated between those two limits as well. All right. So what we're going to do is we're going to take for u, we're going to take t, and then all the rest of this stuff will be our dv. So we'll set u equal to t. So that means du is equal to dt. We'll set dv equal to e minus t over tau times dt. And then we integrate. We've already done that integral. It gave us a minus tau factor, e to the minus t over tau. Okay. So that means our expectation value for the time is we have a 1 over tau that sits out front. And then we're going to do our integration by parts. uv. So u is t, v is minus tau e to the minus t over tau. And now I'm going to explicitly put in the limits that we have to evaluate this over. And then we go minus v du. But v has a minus sign, so we'll get a plus tau integral from 0 to infinity. E to the minus t over tau, and du is just dt. Okay, I guess I can close my brackets. Now, what's nice about really explicitly putting these limits in is that at the limit t equals 0, we get a 0 up front. At infinity, we get infinity times e to the minus infinity. What's that going to be? Which one of these is faster? Which one changes more quickly? The linear t? Yeah. So you have infinity times 0, so that's undetermined. If it's undetermined, like strictly speaking, what is the process for finding the limit? There's a rule for doing that. What is it called? L'Hopital. I'm not going to do L'Hopital, but what you would do is you would take derivatives of these functions, and the derivatives would have the same limit as the original functions. But once you get the hang of it, exponential changes quickly. It goes to 0 much faster than t goes to infinity. And so the exponential dominates. And so at both limits, this is 0. Okay, so then all we need to do is evaluate this new integral. In fact, let's go ahead and cancel the factors of tau. We've already done this exact integral twice. So it keeps coming back. It's minus tau, e to the minus t over tau, 0 to infinity. And now when we put in our limits, we're going to get minus tau, e to the minus infinity, minus e to the 0. This is 0. This is 1. The minus signs cancel. And therefore, the expectation value for our mu1 decay time is plus tau. So when people say that the lifetime of a muon is about 2.2 microseconds, and so when people say the muon lifetime is 2.2 microseconds, what they really mean is that if you were to measure a whole bunch of muon decay times and average that, you would get tau. The actual lifetime of any individual muon could be anything. So if we plot the exponential distribution, it looks something like this. And so what this is telling us is that, so this is P of t. The most likely lifetime for a muon that you happen to capture, and then you're going to measure its decay time, most likely it's going to decay almost instantly. But the average value, the mean lifetime, sits right here at tau. Okay, good. So let's keep going. Let's try, keep writing x, but we're thinking about time right now. Now I want to calculate the mean of t squared. And so all we're going to do is keep doing the same kind of integrals. 0 to infinity. So our normalization constant was 1 over tau. We're going to have a t squared, e to the minus t over tau dt is what we have to evaluate. This is another integration by parts problem. Okay, so we'll do u is t squared, du is going to be 2t t. V, or dv, is the same as before. So that's exactly the same. V is still minus tau, e to the minus t over tau. All right. So the mean of t squared, we're going to have a 1 over tau. And then we have our uv. So u is t squared. V has a minus tau, e to the minus t over tau, 0 to infinity. This still goes away. T squared goes to infinity faster than t, but it's still not as fast as e to the minus t over tau goes to 0. Okay, and then we have minus the integral of v du. Again, we'll have this minus tau factor, so we end up with a plus tau. Integral 0 to infinity. And let's see, we have to put in, we'll have a du, it's going to give us a 2t. So let me put the 2 over here, I'll put the t here, e to the minus t over tau dt. Okay. What is this? We've already seen it. Let's go back here. The integral of t, e to the minus t over tau. We've already done that, and we see it again here. If I had a 1 over tau, this would be the expectation value of t. So what this really is tau times the expectation value of t. but we already know the expectation value of t is tau, so this is a tau squared. Okay, so therefore, what are we left with? This term is 0. We have tau and tau that are going to cancel, so we just get a 2 times tau squared. 2 tau squared, I do believe. Okay, so now that we have the expectation value of t and of t squared, we can calculate the standard deviation or the spread of our distribution, the spread of lifetimes of the muon. So what determines really what the spread is going to do is it's going to determine how wide is this exponential. I could have an exponential distribution that does this, and I could have one that does this. And so it's the standard deviation that's going to tell us what that width looks like. But this is now easy. We've done all the hard work. So the standard deviation squared, standard deviation squared is equal to the expectation value of t squared minus the expectation value of t squared. And we've worked these out. This is 2 tau squared minus tau squared. And so we just get tau squared. And so therefore, the standard deviation is the square root of that, and it's just tau. So for our exponential distribution, we found that the mean value and the standard deviation are given by the same parameter tau, which represents the average lifetime of our population of decaying particles. Okay, so we're going to do these kind of calculations in this course, but our probability distributions will be determined from the square of some wave function that we get by solving Schrodinger's equation. Okay, any questions? All right, so what I want to do is move on to our last topic in chapter 1. And so your assignment will be based off of chapter 1 material. All right, so we are in section 1.5 of Griffiths, and we're going to talk about momentum. So far, all we've really been able to do is associate wave functions with the square of a wave function with a probability density that tells us where we might find a particle. And then we figured out how to calculate some expectation values that are associated with like position. So what if we wanted other dynamical variables? So having identified the wave function as a probability amplitude. So just some terminology. You will often hear, or you will sometimes hear, the wave function called a probability amplitude, and then the square of the wave function as a probability density. Okay, so there's a distinguish between those two. It's a bit like if I had an electric field, it would have some amplitude, say it's oscillating at some frequency, visible light or whatever. We would say that electric field has some amplitude. If I square it, I get an intensity. So that's sort of the distinction. All right. So we've identified the wave function as a probability amplitude, and we developed some formalism. Develop the formalism of calculating expectation values and we just did an example of such a calculation, we can find the average position via the expectation value of x is the integral from minus infinity to infinity of x times our probability density, which we get by squaring the wave function. Okay, so we now attempt to calculate other dynamical quantities. Specifically, the one that we want to look at is momentum. So specifically, the momentum. Okay, so the way we're going to do this, I'm just going to restart my little tablet thing here. It's it has a big delay, which is annoying. The way we're going to do this is we're going to recognize that if I know something about the position, the way I can get velocity is by taking a time derivative of the position. And then once I have velocity, I could just multiply by m, and that will give me my momentum. Okay, so we start by assuming that the time derivative of the expectation value of x gives the expectation value of velocity. Okay, so we're going to make the assumption that we can do a calculation like so. So this is really a postulate. We postulate that this procedure gives the right expectation value for V. Okay, so what we're going to have to do is we're going to have to use, for the expectation value of x, we're going to have to use this expression. Okay, all right, so that means V is equal to d by dt, the integral from minus infinity to infinity of x times the square of the wave function, but I'm going to write the square of the wave function as the wave function times its complex conjugate. Okay, so let's just emphasize that this is the complex conjugate of psi. So the way you would find that is you'd write down your expression for the wave function, and wherever you see a I, you would just change it to a minus I. That's what the complex conjugate does. Before we actually do this derivative, let me just emphasize that this x is not a time-dependent position of our particle. It is an integration variable that we're going to integrate over all space. So when we take this derivative, it acts on these two factors, not on the x, which is like a dummy integration variable. Okay, so let's just note that x is an integration variable, not a time-dependent position. Whoops. Okay, so now what we have to do is we say, well, okay, V is going to be equal to the integral from minus infinity to infinity x, the time derivative is going to pass right by that x, and it's going to act on these wave functions. I'm going to put the conjugate one first, like so. Doesn't really matter. And so what we're going to have to do is we're going to have to use the product rule. Okay, so let's just write out the product rule. Okay, so the first thing we'll do is we'll take the derivative of the first factor. It's the conjugate of the wave function. So it's going to be d phi star dt, and then it has to multiply phi. And then we're going to go plus phi star, and now we act on the second factor with our derivative. So it's d phi dt. And then we're going to integrate with respect to x. All right. So here's the next little trick. This is a bit of a mess. It'll get messier before it gets better. But what we're going to do is we're going to recall the time or Schrodinger's equation. So let's recall Schrodinger's equation. It is essentially the first thing we wrote down at the start of the term. It's like our axiom of quantum mechanics. And it was that the time derivative of the wave function was equal to, I guess these should really be partial derivatives because phi is a function of position and time. Let me be more careful with my notations. Okay, so we'll write these as proper partial derivatives. Okay, so the derivative of the wave function with respect to time is I h bar over 2m. Two derivatives with respect to position minus I h bar potential times the wave function. So what I want to do is where I see this time derivative, I'm going to replace it with the right-hand side of Schrodinger's equation. So this is going to replace this. Now what I could do is I could take the complex conjugate of this equation. So let's take the complex conjugate. So we'd have the time derivative of the conjugate of the wave function is equal to all of the stuff after I take the conjugate. So phi is going to become phi star, and we're going to reverse the signs in front of these i's. So we're going to get a minus I h bar over 2m. Two derivatives of phi star. And then we're going to get plus I over h bar potential phi star. Okay, and so what we want to do is make the same kind of substitution that we're going to make for the first one. Okay, so let's see what happens when we do that. Okay. So we were calculating the expectation value of the velocity. We had the integral from minus infinity to infinity of x times, let's have a look at it. There was, okay, first we have the derivative, time derivative of the conjugate. And so that's going to be this orange stuff here. So we get, why do I think I'm a little confused. I see a sign problem, but let's go forward here. Okay, so all right, so I think it's minus I h bar over 2m, and then it's oh, okay. Yeah, let's just write it out. Okay, so it's d2 phi star dx2 plus I h bar v phi star. And all of that is going to have to multiply 5. Okay. And then we have plus phi star. And then we have what's underlined in blue. So I h bar over 2m d2 phi dx2 minus I h bar v times phi. Hopefully this is going to work out. We will find out. Okay. And then this is all integrated with respect to x. All right. So what do we get? Integral from minus infinity to infinity of x. All right. So I'm going to write this term first. We're going to have phi star and an I h bar over 2m. So I h bar over 2m phi star. And then it multiplies this derivative. d2 phi dx2. All right. The next thing I'm going to do is I'm going to write down this term. It's going to be an I h bar over 2m, which we already have, but there's a minus sign. And so that's where this minus sign comes from. Okay, and then that's going to multiply by phi. I'm going to put the phi first. And then we have two derivatives of phi star. Okay, good. I was worried, but I think this is going to work out. Now what we have left are the potential terms. So we have a plus IH bar. So that's I over H bar times V. And then notice I got phi star times phi. But phi star times phi is just the absolute square of the wave function. And then when I do this one, I get the same thing. I over H bar times V times phi squared, but the sign is reversed. So we'll get a minus phi squared. And then we close our bracket and we do dx. So, of course, this term cancels. All right. So then our expectation value for the velocity is going to look like, let's see, we have an IH bar over 2m. That's all a constant. The integral from minus infinity to infinity of x. And then I'm just going to copy down what's in these brackets exactly as it is. So phi star, two derivatives, minus phi, two derivatives of phi star. All right, so this still looks a little messy. So we're gonna do a little trick. And so the trick is the following. I'm gonna claim that what's in the brackets here is the same as d by dx of phi star d phi dx minus phi d phi star dx. Okay, let's just confirm that it actually is the case. And so we just have to do product rule again. maybe you can see quickly that it is actually going to cancel. It's going to work out because we have cross terms where I'm going to have one derivative of phi times one derivative of phi star minus a derivative of phi times derivative of phi star. So those are going to cancel, and it's only the second derivatives of these terms that will survive. But let's just do it. So it's d phi star dx d phi dx plus phi star d2 phi dx2. That's the first term. Then we'll get a minus d phi dx d phi star dx. There should be a cancellation right here. And then we end up with a minus phi d2 phi star dx2. And these two remaining terms are exactly what's in the brackets here. So what we're left with then is this expectation value is I h bar over 2m, the integral minus infinity to infinity of x d by dx of phi star d phi dx minus phi d phi, that's not a second derivative, it's just one derivative, d phi star dx. All right. So what do you suppose we should do to go further? We just did integration by parts in our probability distribution example. Here, I have some x that we can identify with u. And then I have an exact differential. I have d by dx of some stuff times dx. So this stuff is just our dv. So let's do it. So we'll say integrate by parts. We'll say that u is equal to x, so du is equal to dx. And we'll say dv is d by dx of all the stuff dx. So that means v is just equal to all that stuff. So let's try to evaluate. So let's see, therefore, v is u times v. Okay, so it's x times phi star d phi dx minus phi d phi star dx, evaluated between minus infinity and infinity. That's just the uv part of it. We still have to do the integral of v du. What's this going to be? If somebody asks you what something complicated is going to turn out to be, what is it usually going to be? It's usually going to be really simple, like 0, right? Why would it have to be 0? Can you think of any kind of restrictions on phi? What's that? Yeah, the wave function goes to 0 at plus minus infinity. Why does that have to be the case? Because if I drew some wave function squared as a function of position, if I made it like some arbitrary thing where it doesn't go to 0, then I can't possibly satisfy normalization, which requires that the area under our function equal 1. How could the area be equal to 1 if our wave function is not vanishing at plus minus infinity? So that's an important point, and so I'll try to emphasize it. So we require phi go to 0 as x goes to plus minus infinity. If that wasn't the case, then we cannot normalize such that the integral of minus infinity to plus infinity, of phi squared dx equals 1. All right. So if the wave function phi goes to 0 at plus minus infinity, so does its conjugate. And so all of this is just going to go to 0. And we still have to do, I should have probably left myself some more room. We still have to do the v du part. Oh, that's no good. Let's try that again.
The I tomorrow.
Yeah, I might have missed it. We'll have a look here in a second. Yeah, you're probably right. It's not actually going to matter because we're throwing this whole term out, but we should do it correctly. Let's see. Integrate by parts. Yeah, so you're right. So this is still going to have a factor of I h bar over 2m. And that's going to multiply also the v du that we're about to do. So then we have to do minus the integral from minus infinity to infinity of v. V is everything that was in the square brackets. And so let's get that back on the screen. It was phi star d phi dx minus phi d phi star dx. Okay. And then du is simple. It's just dx. So we'll have a dx here, like so. All right, so we're making some progress. If you want to see what progress we've made, if we go back to here, we started with, where is it? We started with this mess of second derivatives. So we've done one cycle of integration by parts, and we've gotten down to a single derivative with respect to x. Okay, so let me just copy this down. I'm going to try to write it nicer. So far, we have the following. So we're calculating the expectation value of v, and we have got it to the point where it is minus ih bar over 2m integral of minus infinity to plus infinity star d phi dx minus phi d phi star dx integrated over x. Okay, good. So what we're going to do is we're going to work on just the second term of this expression. It's this integral, and we're going to do another integration by parts. So we're going to use integration by parts again, but only on the second term. Okay, so I want to focus on the integral of phi d phi star dx dx. So maybe I won't write down all the details. You can do it yourself. U is going to be just the phi, and dv is going to be this phi star derivative times dx. So when we do that, we'll get uv is going to be phi squared between minus infinity and infinity, that's going to vanish for the same reasons we just talked about. And then we would have minus the integral of v du. But if dv is this, then v is just phi star. And du is going to be d phi dx dx. So it's going to be d phi dx dx. And so you might look at that and say, well, what was the use of that? We've just traded a derivative on one of the factors for a derivative on the other factor. But the reason we've gone and done this is because now we've written this so that it looks the same as the first term. So this looks just like this. And in fact, its signs are even going to be the same because I have a minus sign here. It's going to cancel with this minus sign. So these two terms are just going to add together. Okay, and so therefore, we're getting close to our final result. The expectation value of the velocity is going to be minus I h bar over m. I'm not going to write down the 1/2 because these two terms are identical and they're going to add. So that gives me that factor of 2 that cancels with the 1/2. And we have the integral from minus infinity to infinity of phi star d phi dx dx. All right. So what we can do is it's more conventional to write the expectation value of the momentum as m times v. And so that's minus I h bar. There's no m now. We moved it over here. The integral of minus infinity to infinity of phi star d by dx by dx. And so we could stop here and we could say, look, now once you have found your wave function by solving Schrodinger's equation, you would just do this calculation and that's going to give you the expectation value of the momentum. But what we're going to do is we're going to try to write this in kind of a more suggestive, more convenient way. And we're going to try to define these operators, which we're going to use to calculate quantities in quantum mechanics. Okay, that wasn't on purpose, but we'll live with it. So this is the expectation value of the momentum. You know, it was a long-ish derivation, but none of the steps were too difficult. All we did is took a derivative of the expectation value of the position. We applied product rule, and then we did a few rounds of integration by parts. Okay, so to summarize then, now we have found the following results. For x, we calculate x in the following way. Expectation value of x is x times the probability density integrated over x. I'm going to write this in a more suggestive way. I'm going to write it in the following way. I'm going to put phi star here, and then I'm going to put x between phi star and phi. And then we'll write our dx here. So that's the same thing, right? I can move this x around, and then these are still going to collapse into each other and give the square of the wave function. It's just written in a way that's going to be suggestive in just a second. The other thing we have found is that the momentum is minus I h bar, integral from minus infinity to infinity. It's right at the top of the screen here. Look, it has the same sort of structure. It has phi star and phi on either side of something in the middle. So it's phi star. And then there's something between them. This time it's a derivative. And then we have phi dx. This time, however, I can't just arbitrarily move this thing around. It's a derivative. It's acting on this phi. I can't just rearrange these terms. I can do it for this one because this is just multiplying by x. In quantum mechanics, what we find is that expectation values are always of this form. It's an integral between phi star and phi with some operator between the two. If we're finding the expectation value position, the operator is just multiplying by x. If we're looking for the momentum, the operator is I h bar with a minus sign times this derivative. In fact, maybe what I should do is I should write this in the following way. I should put the minus I h bar in here and have the integral from minus infinity to infinity of phi star minus infinity to infinity. Okay, good. So in quantum mechanics, the stuff in the brackets are called operators. We use a hat notation to identify objects as operators. Okay, so the position operator is just x. Okay, so that means x hat. That's going to be our operator notation. It's just equal to x. So that one's not so interesting. Nevertheless, that's what it is. That's simple case. The momentum is a little more subtle. The momentum operator. So far, everything we've done is just one-dimensional. So I'll emphasize that this is in 1D is the position derivative with some other factors. Okay, and so the way we would write that down is the momentum operator. I'll write that as p hat. And it's just everything in these green brackets. It's minus I h bar d by dx. Minus I h bar d by dx. So just thinking ahead, if we were working in 3 dimensions, how do you think this momentum operator would change? What's that?
Gradient.
Yeah, exactly. That's right. You could replace this with the gradient, which is going to be a single position derivative along each component in space. Whether you're working in Cartesian or spherical or cylindrical coordinates, you just pick the gradient with the right set for the correct coordinate system that you're working in. All right, so those are the 2 kind of most fundamental operators that we'll deal with. There are other dynamic variables, and they can be expressed in terms. of position and momentum. And so I'll give you some examples of that. Okay, so for example, how are we doing time-wise? Okay, we got like 20 minutes. So for example, if you wanted angular momentum, it's the cross product between position and momentum. So we could write down a three-dimensional position operator and a three-dimensional momentum operator, evaluate the cross product, and now you have the operator for angular momentum. The kinetic energy is p squared over 2m. That's the same thing as 1/2 mv squared. Okay, so let's do the kinetic energy. So this is kinetic energy. Okay, so I want to consider our operator for the kinetic energy operating on some wave function. Well, that's going to be 1 over 2m, and then we have to have the momentum operator twice. And so then that's going to act on our wave function. So I'm just going to substitute in our momentum operator. I'm just going to write down minus IH bar d by dx twice. So it's equal to 1 over 2m minus IH bar d by dx minus IH bar d by dx acting on our wave function. Okay, let's see. Minus signs cancel, but then we have I squared, so the minus sign comes back. So we have minus h bar squared over 2m. And then we have two derivatives with respect to position acting on our wave function. Do you remember seeing this anywhere? Where have we seen that?
Let's term on the right-hand side of the Schrodinger equation.
Yes, that's exactly where we've seen it. So we wrote down Schrodinger equation somewhere, didn't we? Oh, where the hell is it? Oh, did we not have it? Okay, I'll just write it down again. So let's compare to the Schrodinger equation. And you're exactly right. That's exactly where it appears. So the Schrodinger equation was IH bar d phi dt. That's the left-hand side. But on the right-hand side, we had minus h bar squared over 2m d2 phi dx2 plus v times 5. And so now what we're saying is that if I take my kinetic energy operator and act on the wave function, it's exactly equal to this. So this term here is the kinetic energy term in our Schrodinger equation. And then here we explicitly see the potential energy. And so we have kinetic plus potential multiplied by this wave function is equal to the stuff on the left. And so this is like our mechanical energy of our quantum system. All right, so this is the kinetic energy term. And this one is our potential energy term. Okay, so it is common to write a new operator h hat is equal to t hat plus v hat, where v hat is just going to be the potential energy. So our potential energy operator is just a v. Okay, the reason that they give the symbol h is because when you take the advanced mechanics course next term, that's physics 328. You'll talk about Hamiltonians, and Hamiltonians are the sum of kinetic and potential energy. And so this is our Hamiltonian for our quantum system. So H hat is called the Hamiltonian. And in fact, a shorthand way of writing Schrodinger's equation is the following. So therefore, Schrodinger's equation can be expressed as, the left-hand side doesn't change. I h bar time derivative. But now we could say the right-hand side is just the Hamiltonian, which is the sum of the kinetic and potential energy operators acting on the wave function. Okay, good. How are we doing here? 10 minutes or so. Does anyone have any questions about any of this stuff? Your first assignment will be dealing with like calculating expectation values and things like that, and doing some manipulations of some wave functions that are given to you. We're about to transition into chapter 2, and then chapter 2 is going to be about actually writing down some actual potentials so that we can write down some of these differential equations that are given to us by the Schrodinger equation and start solving them and finding our own wave functions. Okay, so let's start chapter 2. So we're gonna jump into chapter 2. And the first topic are the so-called stationary states. So what we're going to try to do is we're actually going to try to come up with a simpler version of the Schrodinger equation. One of the challenges right now is that this is a partial differential equation. It involves time, and it involves two derivatives of position in the kinetic energy term. And that's in general pretty difficult to solve. So we're going to look for ways to simplify how we approach finding wave functions. All right, so that's a little bit of motivation. The goal in quantum mechanics is to use Schrodinger's equation IH bar, I'll write it out fully, minus H bar squared over 2m, two derivatives with respect to position, plus v times 5. Let me call this equation 1. To find phi of xt for a given potential energy. In general, that potential energy could be a function of position and time. It might be evolving in time. And when that's the case, that's a beast of a problem. So we're going to look for some simplifications. We will almost always assume that the potential is independent of time. Okay, and so what that means is that this general v of xt, we're going to assume that it depends only on position. And so what we're going to try to do is take this time-dependent Schrodinger equation and write a version of it that doesn't depend on time at all. Then we'll have moved away from partial differential equations that involve mixtures of time and position to something that is only a function of position, an ordinary differential equation that's easier to solve. Okay, so the strategy will be to use separation of variables. In which we assume that the wave function, which is a function of position and time, can be written in the form it's going to have some phi of x. So let me emphasize here that this is uppercase phi and this is lowercase phi. So they're different. And so these little bars on the top matter. Okay, so the lowercase phi is going to be a function of only position, and uppercase phi will be position and time dependent. And then we'll have another Greek symbol. So I guess I should psi and phi. So they sound similar. All right. So that's going to be the strategy. In the end, what we're going to find is the following. We will use these so-called separable solutions to reconstruct the most general solutions to Schrodinger's equation. Okay, so let's just jump in here and see what happens. So on the left-hand side of Schrodinger's equation, we have a time derivative. So if we're going to use separation of variables, then the time derivative is only going to act on the time-dependent part. So we'll have our position-dependent part, and then we'll have d phi by dt. And in fact, I can write this as an ordinary derivative because now this function phi depends only on time. All right, and then on the right-hand side, we're going to have two spatial derivatives. And those are only going to act on little psi, the position-dependent part. So we'll have the time-dependent part and then two ordinary derivatives with respect to position. And so what we're going to do is we're going to take these and we're going to sub into Schrodinger's equation. So that's straightforward enough. We have an IH bar times the time derivative. Okay. So we get IH bar, and then the time derivative looks just like this. And then on the right, there's like a minus h bar squared over 2m, the kinetic energy term, and then two derivatives with respect to position gives us this. So we have phi d2 psi dx2, and then we had our potential energy term. So we just replace capital psi with lowercase psi and phi. Okay, good. Now, if you've done separation of variables before, which I assume you did it in, what is it, Math 225 or something? What you do after subbing in your separation of variables is you divide by that product. Okay, so let's divide by this product. Just for any of you that are in 301, you're also going to do separation of variables to solve problems in E&M. So it's worth knowing the technique because it shows up in many places. All right, so we divide. Oh, okay. So for the first term, when I divide by this product, I cancel here and I get a 1/5. So we have IH bar over phi d phi dt. Okay, and then this time this thing's going to cancel. So we'll get a minus h bar squared over 2m, 1 over psi d2 psi dx2. And in the last potential term, both of these things cancel. So we just get plus v. All right, and remember, our assumption is now that this potential is a constant in time. It depends only on position. Depends only on x. And so everything we're doing now relies on that assumption. Okay, so we have a couple minutes left, and let me just recognize now that what we've done is something very handy. We have written this expression where all the time-dependent stuff is on the left, and all of this is independent of position. This function depends only on time. There's no x anywhere. On the other side, on the right, we have things that only depend on x and have no time dependence. So so maybe I'll emphasize it this way. Function of t only independent of x. And this is a function of x only. It's independent of time. Okay, so if you think about that for a second, that has some consequences because what I could do is I could sit at some fixed position. Let's imagine I'm at some position in space and I calculate the stuff over here. And I'm going to get some result. And maybe that corresponds to some specific time. And then I allow time to evolve. As time evolves, this is changing. But if I sit at the same position, this is the same constant. So the only way this equality can hold is if both of these are equal to the same constant. That's part of the heart of this separation of variable technique. And it's the reason that we divided by that product, is so that we could move all time dependence to one side and all position dependence to one side, to the other side. So the left-hand side, and this will be the last thing we write down. The left-hand and right-hand sides must be equal for all combinations of x and t. This is only possible if both sides are equal to the same constant. We'll call that constant E. we'll see why we're calling it E next time. So I think that's where we're gonna stop for today. What we'll do when we meet, I guess Monday is the next time we meet. We are gonna set the left-hand side equal to E, and we're gonna set the right-hand side equal to E, and we'll do some manipulations and see where we end up. All right, perfect. Thank you very much.